Hi guys, it's Mr. Mustafa here. In this video we're going to learn how to prove that minus half factorial is equal to square root of pi. And the big question is how. So how we actually prove this is by making use of the gamma function. So we can gamma function, which is represented by this symbol here. So gamma z. You can also choose different alphabets if you like. Now before I continue with this presentation, make sure to subscribe to my channel and like my videos. So let us go and explore the gamma function and prove some results. So the gamma function, which is gamma z, is defined to be equal to integral from 0 to infinity x to the power z minus 1 e to the power negative x dx. Now we need some properties of the gamma function. So what's important to notice is that we have a z here and we have a z there. Now the x boundaries are from 0 to infinity, and we have 1x here, 1x there, and 1x there. Right, so let us go and explore the gamma function and make up some properties. So if I were to go and find gamma 4, and let me go and find what is gamma 5. So using this formula, gamma 4 will be integral 0 to infinity x cubed e to the power negative x dx, and gamma 5 will be integral 0 to infinity x to the power 4 e to the power negative x dx. Now you can clearly see that you need to go and use integration by parts. So let me go and do my integration by parts using the DI method. Right, so I choose my u's as x cubed and my integration as e to the power negative x. Now if I differentiate this, I get 3x squared. If I differentiate this again, I get 3 times 2x. I'm writing it like this because I want you to see a pattern. Then if I differentiate this again, I will get 3, 2, 1, and if I differentiate this, which is 6, I will get 0. You stop at 0. Now if I integrate this, I get minus e to the power negative x. Integrating this again gives me e to the power negative x. Integrating this again gives me negative e to the power negative x. Integrating this again gives me e to the power negative x. Now how it works is that you just multiply across, this times this, this times this, this times this, and this times this. Make sure you to have a 0. That because it's a polynomial, we can integrate continuously until we arrive at 0. So positive, negative, positive, negative. Start with the positive and negatives. So this is just a cheat for integration by parts. So what you can say is that gamma 4 is equal to this times this plus this times this plus this times this plus this times this. So what you can actually do is you can take out e to the power negative x as a common factor. So all I am left with is negative x cubed, negative, then the next one is negative 3x squared by multiplying these two, minus 3x squared minus 3 times 2x, 3.2x, then the next one minus 3 to 1. Right, you can see you're starting off with negative x cubed minus 3x, so all the terms are negative, and we ended up with this, of course, from 0 to infinity. If I substitute infinity inside here, I will get e to the power negative infinity, which is 0. 1 over something very large is 0, so 0 minus 0 times this is 0, minus, if I substitute 0 inside here, I will get e to the power negative 0, which is 1. 1 times minus 6. Right, this is minus 6, which is the same thing as saying 3 factorial. Right, what if we had to go and do it for gamma 5? So if you have to go and do it for gamma 5, you can see what's happening here. The terms are being negative throughout, and each successive terms are derivatives of each other. So if I have to go and find gamma 5, I can just do this. Let's see. So di method, differentiate, integrate. So x to the power 4 e to the power negative x, so 4x cubed 4.3 x squared 4.3.2.x 4.3.2.1 and then 0 here. So we have negative e to the power negative x, e to the power negative x, negative e to the power negative x, e to the power x, negative e to the power negative x. And if you had to go and find gamma 5, similarly we will get e to the power negative x, as you can see here. This times this times this times this times that. Alright, so plus minus plus minus plus. Let's see, if I take out e to the power negative x as a common factor, all my terms are being negative, right? Perfect. So what I have here is e to the power negative x. I've got negative x to the power 4 minus 4 x cubed minus 4.3 x squared minus 4.3.2 x minus 4321. And similarly, compared to the previous one, all I am left with is 0 minus 4321, which is equal to 4 factorial. So we can generalize. What we know is that gamma 4 is 3 factorial and gamma 5 is actually equal to 4 factorial. So in general, what we can say is that gamma z is equal to z minus 1 factorial, which is 1 less. It's kind of like number patterns. So you have gamma 4, which is 3 factorial, and gamma 5, which is 4 factorial. So how about proving it for a general case? What if you had to go and say what is gamma z plus 1? So to find gamma z plus 1, we know that this is z factorial, but z factorial is also z into z minus 1 factorial. So which is z into gamma z. This implies right. So we are back. So what we've said that gamma z plus 1 is actually equal to z into gamma z, because we can of course use integration by parts repeatedly. So if you have to do this, what you can actually say is, for the general result, it's actually a gamma function. So for a general result, what you can actually say is gamma z plus 1, which is equal to integral 0 to infinity. Remember, we're finding z plus 1, so in the place of z we're going to substitute z plus 1 minus 1, which is x to the power z e to the power negative x dx. Now if I have to go and use that differentiate integrate method for this, right, what you will actually get is, of course, you can factor out e to the power negative x. That's gamma z plus 1. You can factor out e to the power negative x, and what you will have inside here is a bunch of x to the power z, all negatives, minus z into z minus 1. Sorry, the first derivative will be, your first derivative will just be z into z minus 1 to the power. Remember, these are derivatives of each. So negative z into x to the power z minus 1. And you continue with all the negatives until you end up with z factorial from 0 to infinity. Right. So what you actually have here is 0 minus z factorial, which is equal to z factorial. This implies gamma z plus 1, which is equal to, remember, differentiate, integrate was negative x, and of course you'll end up with a 0 right at the end, and just before 0 you'll have z factorial. Right, so z plus, let us get back to gamma z plus 1, which is equal to z factorial. And as I said above, z factorial is z into z minus 1 factorial, which is z into gamma z. Perfect. Right, so what's this property here? This result here is very important because we are going to use this result to find gamma 3 over 2. Now gamma 3 over 2 is actually gamma half plus 1, which is equal to half gamma half. Why you say half gamma half? Because this half is like your z. Remember, comparing from here to there, see, you have z plus 1, z gamma z, because so all I have done is for gamma 3 over 2 I broke it up into half plus 1, for the plus 1 here, plus 1 here, so I've got half gamma half. Now so let us look at gamma half. What is gamma half? Right, so gamma half is equal to, substituting in the gamma function, 0 to infinity, x to the power half minus 1 e to the power negative x dx. So what we have is 0 to infinity x to the power negative half e to the power negative x dx. We can use integration by parts in here. So what I can say is, remember, my final derivative should be x to the power minus half, so I can get rid of this x to the power minus half, which is causing a problem. So I will say let u be equal to x to the power half. So when I differentiate this, I get du, which is equal to half x to the power minus half dx. So this implies that x is equal to u squared, squaring both sides. And the bounds of integration, what we can say is, as x approaches infinity, what we have is u approaches infinity, and as x approaches 0, what we have is u also approaching 0. As x approaches 0, u also approaches 0. So gamma half now becomes integral 0 to infinity x to the power minus half dx cancels out, which is just 2 du from this equation. So 2 du, and e to the power minus x. This minus x is u squared, so e to the power minus u squared du. Now what we have here is a famous Gaussian integral, right? So what we can do here is we can square both sides. So to solve this integral, if we square both sides, we can say gamma half all squared is equal to, so we are squaring this side, we will get 4 integral 0 to infinity e to the power negative u squared du. Remember, you can also put another variable if you like, so you can multiply it by integral 0 to infinity e to the power negative v squared dv. It's the same thing, which is equal to 4 integral 0 to infinity e to the power negative, combining these two, u squared plus v squared du dv. Now what we can see is a change in variable, we can say let u be equal to r cos theta. You can use polar coordinates and change of variables, and v be equal to r sine theta. So what we know that is u squared plus v squared is equal to u squared plus v squared, r squared cos squared theta plus r squared sine squared theta. We will get r squared. Now uv plane, this is a uv plane, and we are transforming into polar coordinates into our theta plane. So UV plane takes up this entire thing here. So basically your radius goes out and wide from 0 to infinity, right? Your radius goes from 0 to infinity, and your theta is just in this angle here in the first quadrant, so pi by 2. So what we can say is for integral 0 to infinity, no 0 to infinity, sorry. What we can say is for integral (0 to pi by 2) for d theta. For dr, we need to say 0 to infinity of e to the power negative r squared, absolute value of the Jacobian dr d theta. So what is the Jacobian? So the Jacobian for this is equal to partial u partial v partial r theta. So what we have is uv here, r and theta there. So this is partial u partial r. Okay, so let us just use subscript. This is from second year calculus, guys. So what we can say is ur, just for simplicity, let me just write ur u theta vr v theta. So basically the Jacobian will work out to r, but I'm showing you in detail. So ur, so you're finding partial u partial r, which is cos theta, so that will be cos theta. Then partial u partial theta should give you negative r sine theta, differentiating with respect to theta. Then differentiating v with respect to r gives me sine theta, and differentiating v with respect to theta gives me r cos theta. Now finding the determinant of this will give me r cos squared theta plus r sine squared theta, which is just equal to r. So what we have here is gamma half all squared is equal to 4 0 to pi by 2, 0 to pi by 2, 0 to infinity, negative r e to the power negative r squared, r dr d theta, r dr d theta. Now we can split this up by Fubini's theorem. We got 4 0 to pi by 2. We can see this variable and this integral. So d theta times 0 to infinity of e to the power negative r squared r dr. So all we have to do is integrate this integral. So what we have here is let u equal to r squared, so du is equal to dr. That's what I can say here. Du is equal to dr, and integrating the first integral, what I can get is 4 into pi by 2 into, now as as r approaches 0, u also approaches 0, and as r approaches infinity, u also approaches infinity. So the boundaries does not change. So what we know is that, sorry, this is 2r dr, du is equal to 2r dr. So r dr is basically du half du over 2. So I'm done with this, and this is just e to the power negative u. Right, now solving this integral, what we have here is half times, so just pi. Integrating this will give me negative e to the power negative u from 0 to infinity. So what we have is pi into, if I substitute infinity here, I'm getting negative 0 minus, if I substitute 0 here, I'm getting minus 1. So all I have here is 1 times pi, which is equal to pi. So here's it, guys. So what we have is gamma half all squared is equal to pi. This implies that gamma half is equal to square root of pi, which is amazing. In other words, gamma half is equal to square root of pi. Now using the properties of gamma, what we can say is, remember, gamma half is the same thing as saying half minus 1 factorial. We have proved this result, which implies that minus half factorial is equal to square root of pi, and there we have our result. So we just proved now that minus half factorial is equal to square root of pi, or gamma half is equal to root pi. So using this, we can generate some factorials. So example, we can say, what is half factorial in this case? So what's half factorial is just basically half into half minus 1 factorial. So what we have is half into, what's half minus 1? This is basically half into minus half factorial. So half minus 1, which is minus half factorial, but we know that minus half factorial is equal to root pi. So therefore half factorial is just equal to square root of pi over 2. Or if you want to find 3 over 2 factorial, in that case, if you want to find 3 over 2 factorial, what we can say is this is 3 over 2, then subtracting 1 from here, we can get half, and then subtracting 1 from half, we get minus half factorial. So 3 over 2 factorial is basically 3 over 4, and this is square root of pi, so 3 root pi over 4. So guys, going back, have we proved this? We have proved that minus half factorial is equal to square root of pi.